Hi there. So in this video, I am going to wrap up those last three examples in section 5.5 that we didn't get to in class today. So if you recall, we were working on our U substitutions in this particular section and demonstrating that for you. So we had said one of the techniques for a U substitution whenever you had an exponential function was to use either the full exponential function itself or the power on that exponential function. So for this one, since I don't have another e in my function, I'm going to choose to just use the exponent. So I'm going to let u equal 1 over x, which we know 1 over x is the same as x to the negative 1 power. Let's take our du of that. So the derivative of x to the negative 1 would be negative x to the negative 2 dx. So we can think of that then as negative 1 over x squared dx. There's my du. So you can see then, okay, well, I have my, the x squared and the dx, that is squared in the denominator, which is where I have this. The only thing I've created is an extra negative 1. So I could rewrite then this as negative du equals 1 over x squared dx. And then that way, this 1 over x squared, because remember I had mentioned to you in class that if we wanted to manipulate this, we could say, well, this is the same as e to the 1 over x times 1 over x squared dx, still in the integral, all right? So now at this point, we know that e to the 1 over x, we can write that as e to the u, and then this portion here is your negative du, so it's really like a negative 1. So I'm just going to factor that negative 1 out in front like I was doing in class, and then I'm left with the integral of e to the u du. And as we talked about before, the integral of e to the u is always e to the u. I've got my negative out front, so I'm just going to replace my u now, so I'll have negative e to the 1 over x plus c. And that would be our final answer. Okay. Scoot on down then in example 16 and 17, we are going to be looking at some differential equations and just going backwards here. So here they're telling us in example 16 that dy dx, so they're talking about the derivative there. They're saying that, remember, dy dx, that's the same as y prime. Y prime is equal to this function where y passes through the point 0, 4. So it wants us to use integration to solve this, so it wants us to find what y is. So y would be equal to the integral of this y prime, so the integral of 2x over x squared plus 9 dx, right? I'm going to let my u be the denominator there. So u equals x squared plus 9. Du then is 2x dx. That matches up exactly with what we have up there, 2x dx. So then I'm left with then that y equals the integral of 1 over u du. The integral of 1 over u, as we talked about, reminded you today in class that the integral of 1 over u is natural log of u plus c. And then I'll just go in and now from here, because this is wasn't thinking about this one being an equation where we need to solve it. So y passes through the point 0, 4. So let's put this as y equals. I will go ahead and let's replace my u here. So let's come over here. That y equals the natural log. In place of that u, I'm going to put in my x squared plus 9 plus c. But since I've given you this information about this point that it passes through, that's going to allow us to solve for our c value. So what we want to do at this point is plug in our x and y values. So y will be 4 equals the natural log of, plug in your x. So I'll show my work here. I've got 0 squared plus 9 plus c. So I'll have 4 then equals the natural log of 9 plus c. We can get an exact answer for our c, right? Because the natural log of 9 is just a number, so I would subtract the natural log of 9 from both sides. So come over here, then I would say c equals 4 minus the natural log of 9. If you were to pop that in your calculator, it's not going to come out perfect, but we'll say then c is approximately 1.80. So I'll just do a 1.8, probably doing 2 decimal places. Giving us then a final answer of plugging back into this equation now, y equals the natural log of x squared plus 9 plus that c value of 1.8. And of course, in that c value, if you wanted to be exact, we could plug in this entire quantity here, that 4 minus natural log of 9. um, on a tester or on a test, I would tell you how to round, okay, for sure. All right, so then we'll come on down to example 17. In example 17, it says, well, given the acceleration, initial velocity, and initial position of a body moving along a coordinate line at time t, the body's position at time t, I'm sorry, find the body's position at time t. So here they're telling us the acceleration is equal to 16, initial velocity is 4, initial position is 10. They didn't put any units on this, like whether they were meters per second or miles per hour or anything like that. But we will just go with what we have here without worrying about our units. Now, if you recall, whenever we first started talking about derivatives, if you recall, you were given your position function. When you took the first derivative, that gave you velocity. And then the derivative of velocity, or the second derivative of your position function, gave you acceleration. So we're just going to work backwards now that now you know acceleration, and we're going to use integration to get us back to our initial position function. So we know what our a given acceleration is. Acceleration is 16. So the velocity would be equal to the integral of that acceleration. And it tells us to do this with respect to time. So I'm going to say 16 dt. So then I'm going to go from here. Well, the integral of 16 of the integral of any constant is just that constant times your variable of integration. So that would be a 16t plus c. That would be my velocity. Since they're giving me here initial velocity, then they're saying, okay, when t equals 0, then your velocity is 4. So I'll plug that in and show that to you. That gets 16 times 0. Right, and so anything times zeros just goes away, and I've got c equals 4 then. All right, so now we know our velocity equation. Our velocity equation is equal to 16t plus 4. All right, so now we're sitting here at velocity, and we want to go to our position function. So we know then that our position function, s, is equal to the integral of our velocity, 16t plus 4. Still integrating with respect to t, respect to time. All right, so now to take this integral, so s equals integral of, I'm bringing down the 16. Remember, coefficients can always be factored out, so I'm just bringing it down. For this variable here, I'm adding 1 to it, becomes t squared. Reciprocal of that 2, a 1/2, plus I'm bringing down my 4, t plus c. All right, and then lastly, I need to figure out, well, what is that initial position there of c? So it tells us that my initial position, s of 0 equals 10. So at time t equals 0, this would be my position. So I'm going to plug 10 in for s, and then I guess I should have cleaned this up a little bit, but we'll go ahead and make that our 8. In place of t, I'm going to plug in 0 squared plus 4 times 0 plus c. Well, of course, all of those are going to 0, so c equals 10 then. Final answer, we have everything we need at this point. We can say that our position function is equal to, just kind of cleaning this up here, my position function equals that 16 times a half, so that was 8t squared plus 4t plus 10. Final answer. Okay, and now you can work your way backwards now. If you start taking the derivative, so if I take the derivative of s here, that's going to give me velocity, right? So I'd have 16t plus 4. All right, sure enough there. Now if I take my velocity function, I take its derivative of the 16t plus 4, it's just going to give me 16, which is what I was given in the beginning as my acceleration. Okay. All right, well, this finishes up that section. Thanks a lot. Bye.